Today we're going to be looking at mobility of mechanisms. All right, to start off, we're going to define what a mechanism is. A mechanism simply is an assembly of joints and links where at least one link is grounded. Joints, links, where at least one link So a link is defined as solid bodies between nodes or connections. And these connections are with other solid bodies. So and a joint is the connection itself between two bodies. It should be at least between two bodies. Between at least two bodies, yep. And the type of joint determines the magnitude of degrees of freedom. Alright, so we're going to split it up into two. So one will be in the planar or the 2D, and the other will be in the spatial or the 3D. So planar or 2D. And to find the mobility of the mechanism that you have, you can use something called the Kutzbach theorem. So this assembles your links and types of joints and tells you what kind of mobility your system has. So define it as M3, N minus 1, minus 2J1 minus J2. That's key. Where N is your number of bodies or links. J1 is your 1 degree of freedom joints. And J2, you could probably guess it's 2 degrees of freedom. Another way you can write this is also M equals 3 and G minus 1 plus the sum of degrees of freedom. So N is the same, so bodies, links, J1, oh, not J, G is your number of joints, and sum of F1 is the sum of degrees of freedom. All right, what does this all mean? So the mobility of a mechanism just tells you in how many degrees, how many different ways your mechanism can move. So let's say you have a pin joint and a body. This is your ground. and you have a straight bar like this. All right. So counting using the Kutzbach theorem, n, how many bodies have you got? You got 1, which is your rotating piece there, and 2, this is the base, and the base is fixed to the ground, so that will be your second. So n equals 2. 1, 2. J1. J1 is how many degrees of freedom? Joints. How many joints have you got that have 1 degree of freedom? And that's just this pin joint here. 1. And J2, there's no degree, there's no special joints. Right. So M, 3, 2 minus 1, minus 2, 1 is 1. And you could, like, it's a pretty simple question, so you can just guess it right off the bat. Like, you can already guess that it can only rotate about this pin here. That's your simple definition so far. All right, other definitions that you need to know. So J1, these will typically be your pin joints and your sliders. Right? So a pin joint is just that one there, and it can rotate. Or your slider, for example, could be this. And it's a fixed translation, left and right. So that is 1 degree of freedom. That is counted as a joint, right? J2 or 2 doff. So that could be a pin and a slider. So you've got that pin there, which allows for rotation, and one for translation as well. Another note that you need to make as well is the order of joints. So when I say J1 and J2, that's an order. So J1 is a first order joint, and J2 is a second order. And another example of a two-dove joint is something called a half joint. So if you have one body there and another body there, their contact there is something called a half joint. And that would be two-dove. All right, let's try another example. So EG2. All right, who wants to have a go at this? So there's N, J1, and J2. How many bodies do you reckon we have in this question? We've got that, that's one. Are there any others? All right, I'll do this one too then. The second one would be the slider, and the third is your ground. That's 3. How about joints? Yeah, that's right. How many joints do you reckon we have? Yeah, it was. Yeah. 1.5. Why do you say 1.5? So obviously the pin is 1. It's more for that's for rounded joints. That's rounded on another round. 2. So half joint is only the term that I'm using. It actually counts as a 2 degrees of freedom. Yeah, it's a little bit confusing. That's why you said 1.5, isn't it? There's actually no half joints. They're pretty fixed. So M3 minus 1 minus 2 times 2 minus 0 1. Oh no. That's 6 minus 4, so 2. Because looking at this, you can slide it and it can rotate. So that's 2. 2 degrees of mobility. And it's got to be harder. Alright, Simon, this question's yours. No pressure. We're going to pretend that these bodies are attached to the pin. Okay, how's that? Imagine 3 bodies on a pin. Alright, now you guys can see that, right? Okay, let's give it a go. Alright, bodies. How many do you reckon we have? 2? Okay, let's count them. So we have 2 of these bodies, right? Why don't we have 3? Did you count the ground in this one? Nope. So James, it kind of is 4, but you can imagine that these grounds are the same. Yeah. Yeah, that's just one thing that you have to remember. Yeah. Well, it's not really a derp. All right, 3. All right, J1. How many single degrees of freedom joints have we got? And what are they? Yep. And the last one? Last one is 1. Yep. So that's called a half joint because it's not really fixed in one dimension. So M3 3 minus 1 minus 4 minus 1 9 no 0. That's all right. 6 minus 4 minus 1 that's 1. Cool. Next example. What is that, like 4? 4. Take your time with this one. Okay. What do you guys reckon? Just like having a look at this question here. Do you think it'll move or not? If these are solid bodies, let's say they're solid lengths and they can't extend. How many total bodies do you reckon we have? Five. So 3 links and then 1 ground. Yep, we can. Even though it's in different places, they're not going to move against each other. So they can be counted as one body. Yep, cool. 5. How many single joints have we got? So 1, 2, 3, 4, 5. Oh, no. Where did I get this question from? 1, 2, 3, 4, 5. Oh, okay. This one's a bit tricky. So you guys, 3 and 4, is that your guess? Yeah, it's a pin slider. You can count those two as separate ones. If you count that as a separate body. 5. So what? So 1, 2, 3, 4. What do you reckon, Simon? Is that a single or a double? If you have 3 bodies with 1 pin link, how many ways do you reckon they can move? Oh, yeah, okay. That it's definitely more than one because you have 2 bodies, 3 bodies. If you separate a question like this out, let's say, I draw the property. If you wanted to visualize it and you just separate it out, if you imagine this is grounded and doesn't move, you can count that as a single degree of freedom there. So that's 1. And then another one there. So actually, it's 2 single degrees of freedom, right? It's 2 single degrees of freedom. So we count the obvious ones again. 1, which is a slider. 2, which is the pin. 3, 4, 5, and 6. All right. So there's 6 single degrees of freedom. Yeah, I know, right? When I first did this discussion, I was like, whoa, man. And the half joints, there are actually none of those. This may or may not be in your quizzes. M3, 5 minus 1 minus 6. 6 times 2, I think. Or should be 2 times 6 minus 0. 12 minus 12 equals 0. This actually can't move. So it's not obvious at first if you just look at this ugly drawing here. But if you simplify what you've got into pins, joints, and sliders, you can actually find out a lot about what you've got. So this can't move. All right, let's try another one. And then rush it. Oh, I rushed it. That's horrible. What's 4? All right, first off, break it down. N, J1, J2. How many bodies do you reckon we have? 6. So 1, 2, 3, 4, 5. And what's the 6th one? Ground, 4 links, and a slider. Ground. Yep. Does everyone understand where I'm coming from? I don't want to go too fast for starting an actual question. 6. Joints. Single degrees of freedom joints. How many? It's definitely not 2. 7. All right, let's count your 7 then. All right, what are the 7? Did you just call Rampton an idiot? That's a big oof for me. All right, let's give it a count. So the obvious ones, obvious, your slider, A, right? And then you've got another pin there, B, C, D, E. So they're all simple pins. 1, 2, 3, 4, 5. Right, 1, 2, 3, 4, 5. And then F, G. That's 7. 1, 2, 3, 4, 5, 6, 7. You shouldn't put yourself down like that. It's 7. So M, 3, 6 minus 1 minus 15 minus 14 equals 1. Yeah, tricky question, isn't it? Let's do another one. 1, 2, count that right? 1, 2, 3, 4, 5, 6. Yeah. Cool. Cool. All right. All right. How about this one? E.g. whatever. So this can rotate, and it can slide as well. So let's assume frictionless. And J1, J2. What do you reckon? It actually doesn't, because it's got that rotation aspect. So bodies, let's count. 1 for ground, 2, 3, and 4. So the definition of a link is a body that's got connections to another body. So if this body is connected to the ground, that counts as 1. So 4. J1, 1, 2, and 3. So you can't count the connection between the slider or the wheel and the ground because it's not one dimensional. It rotates and it slides. That's the same as a round shape there. It's not like a fixed joint. Does that say no friction? Yeah, it did say no friction. If there was friction, it's 3 off if friction. Do you reckon? I could be reading my question wrong. So I wanted to, wouldn't it be like, could be right. I'll have to review that. Okay, last question. Before we start with the tutorial, let's go with a big ground and behind it. Ah, what do we reckon? I do have a bit of French in me. All Vietnamese people do. So yes, it is a baguette. Yep. So what's that? So the wheel, the ground, and the baguette. Oh, I wrote N there. J1. do we think that this is a single degree or 2 degree? Yeah, the connection between that is the 2 degree. So we've got 2 pins, that's J2 of J1, 1, 2, and your 2 off is that round connection with that. Alright, I think that's it for the practice. I'll set out some more definitions for 3D too. So for spatial, so that was planar. That's in 2D space, but for 3D space, we've got other definitions for it. So instead of a 3, which is the total number of degrees of freedom in a 2D space, so 2 translation, 1 rotation. In the 3D space, we have 6, because that's 6 stuff. 3 rotation. X, Y, Z. And 3 translation. All right. So your mobility formula is simply 6n minus 1 minus 5 times J1, 4, J2, 3, J3, 2, J4 minus 1 times J5. So you can already guess J5 is a joint that allows for 5 degrees of freedom. Or similarly with the first one, so N is your number of bodies or links, G is your number of joints, and Fi is your sum of degrees of freedom. So examples of J1, so that's also your pin or your sliders. Where is or you can also call those revolutes. So these would be special pins and sliders. So in the 3D space, let's have a that would be where your translation is limited. Or you can only rotate. That's your revolute joint. Or another one in the 3D space would be if you had that and it's fixed rotation, only slider. Yeah, linear rail is a good one. So J2 cylindrical. So that's if you had a cylinder on a rail and it's not restricted in rotation. So free trans, free rotate. Another one in the 3D space would be if you had a plane and you had, let's say, a box. That's horrible. Ah! Because it can translate in the X and Y but not the Z, that's a J2 because it can only allow for 2 degrees of freedom, right? The last main one I'll define for you is your spherical. So spherical is if this is fixed, but if it's fixed in the translation, but it can rotate. Those are the main ones. Once you encounter a problem, you just have to define which ways, in which degrees of freedom it's free to move in. Define joints as in cool. How are we on time? 12:40. That's not too bad. All right. So we've got 2 questions here. One is in the planar. One is in the spatial. Chat. Whatever. All right. To make it easy, we'll just do question 2 first because it's in the planar and we haven't had any experience with 3D yet. Q2. All right. It says use the planar mobility criterion m equals 3 and minus g minus 1 plus sum of f to show that the total mobility is 1. So the question's asking you to prove m equals 1. You can actually do that using either formula, but it's asking you to do that. So let's do it. So n is j1, j2. And we'll convert that to g and sum of f. Let's have a look at this umbrella. So everyone knows how umbrella works. You hold the handle and you slide this up and down. And what's going to happen to your umbrella? It folds in and out, right? But with this mechanisms question, we are only dealing with links and joints where at least one link is grounded. So for this example, we have to assume that the handle is grounded because when you're using an umbrella, you hold the handle, obviously, right? So let's do that. Let's define this as cool. Yeah. Sweet. All right. How many bodies have we got? So we define this as 1, and that counts the top of the umbrella as well. So this whole body there counts as 1. How many more bodies have we got? Ooh, 4. What are your 4 bodies that you're counting? Are you counting 1, 2, 3, 4? I'm counting 6 as well, because you have your 4 rigid bodies, 1, 2, 3, 4, but you have to count the connection between this body and the uni body itself. So this part there counts as a solid body because we defined a body as a link as a body that connects 2 bodies. 2 sliders, 3 arms, and a center rod. Yep, cool. I'm happy with that. What else have we got? It is a slider. We're defining the handle as a ground. Oh, 1, 2, 3, 4, 5, 6. Yeah, it's an unusual umbrella, isn't it? Has 2 sliders. We can neglect the spring as well, that doesn't count. But we've got 1, the umbrella whole body, 1, 2, 3, 4, and 5 and 6 are the non-obvious ones. Let's go with joints. How many single degree of freedom joints have we got? Six J1s. All right, let's count. Simon says 3 because he reckons these are 2 degrees of freedom, aren't they? All right, let's give that a go then. So if your formula is M3N, let's say this is test minus, what did you say, 3? 3 times 2 minus 2 times 1, where n is equal to 6. We both agreed that n is 6. Do you reckon that makes sense? Do you reckon there's 7 ways that you can move this umbrella? They actually count as 1 degrees of freedom. It only counts as a 2 if it's separated. So we've actually got, we've got 1, 2, 3, 4, 5. Yeah, it is pretty mindfuck, isn't it? So we've got 5 pins, right? 5 pins and 1 doff. 5 pins and 1 doff sliders. You guys are thinking too hard. We don't actually have any of these. So we have 7. I know I'm all over the place. Sorry, 6 bodies. 15 minus 14 equals 1. We did it. Isn't that a pin slider in the middle? So you reckon 5 and 6 are pin sliders? Yep. So where 5 is, you have a pin and a slider. But next, yeah, it is 2. Okay, so I'll count the single degrees. So I'll count the pins first. 1, 2, 3, 4, 5. So you said next to number 4 there's 2 J1s. Yeah, that's right. So 1 and 2. 1, 2, 3, 4, 5. And there's 2 sliders. Now I'm only counting 2 sliders. Sorry, so do you agree that 5 and 6 are sliders? Where's the other slider that you're talking about? Ah, no. That's that's fixed to this arm here. Yeah, so that doesn't translate. Okay. So if we wanted to do it the way that the question asks, so it says M3 n minus g minus 1 plus sum of f of I. So All right, N6, J1 equals 7, J2 equals 0. N equals 6, yep. G is the number of joints, so we have 7 joints. And sum of f of 1 is 1 plus 1 plus 1 to the power of 7, so that's 7 as well. So 6 minus 7 minus 1 plus 7 equals minus 6 plus 7 equals 1. So we get the same thing. Cool. All right, let's go to the 3D question. All right, so we have platform A, which is attached to a fixed frame or your ground via 3 links, a bottom platform, which is attached directly to the frame. The 3 links are attached to a platform A and to the frame via cylindrical joints, allowing rotation, sliding, yada yada yada. Bit trickier. So 3D. So M equals 6. This one's a little bit harder. And let's try count the bodies. What's the first obvious body? When we're looking at mechanisms, what do we look for first? We look for a ground, don't we? And what's our ground in this situation? Well, ground, the first one. I should draw it. Yep. Frame. 1. What's another link that we have? Remember, our links are these solid bodies that connect nodes or connections. What's another one that we've got? Would this plane, do you think that would be one link? One body? Yes. So in the previous question, when we had a pin and slider, there was a body connecting between them, right? And we counted that as a link. Do we have anything similar to that in this question? We do. We have lots of them. There is 3 of them. 1, 2, 3, 4, 5. Do we have any more bodies that anyone can see? Or we counted them all? I'm going to say no. I can't see anymore. Okay, let's count the joints. What are some joints that you guys can see? Just looking at the question. Ooh, you could do that. Or you could hop onto SolidWorks and build it there. All right. The first obvious joint that I can see are these 4 here. So in the 2D space, that would be in the 2D space, these would be pin joints, right? But because this is in the 3D space, you have 4 more degrees of freedom. So we have 2 more degrees of freedom in rotation, and that makes these sphericals. And we have 4 of them. So 4 sphericals, and they're actually you can't translate these against another body. You can only rotate them. So we have 4 times J3, right? Sphericals. What else? What else have we got? So if these joints here are cylindrical joints, what can they do? Okay, that's one aspect of it. It can slide. Yeah. So what's the degree of freedom for those? Yep. Cool. And how many of those? Right. 3 times J2. Cylindrical. And do we have any other joints? So we have 1, 2, 3, 4, 5, 6, 7. So Kutzbach theorem, M equals, so J3 and J2, that's what we've got. You can cross that out, that and that. 6, 5 minus 1 minus 4 times 3 minus 3 times 4. 6 times 4 minus 12 minus 12. So what does that tell us? It can't move. But we're not wrong. So something like that isn't obvious unless you make it in Gary's mod, or you sum up all the degrees of freedom and the lengths, chuck in the formula, and you can find it out. All right. The second part of it says, if instead of cylindrical joints, ball joints were used, what would the mobility of the platform be? So, part B. So, originally we had NJ 25, I think. 5, 4, and 3. So they said if cylindrical joints were changed into ball joints, so we had J3 equals 7, because we're just converting these to a 3-DOF, N would be the same. What would the Kutzbach theorem tell us? No, they can't. They'd be like fixed in a socket. Do you think that helps anything move? So if we recalculate it, 6 n minus 1 minus 4 times 7, I think. It's 4 times 7. Uh, 24 minus, how can I do that in my head? Sorry, it's 3. It would be 3 times 7. Because it's 3 times J3. Yeah, that's right. 24 minus 21. So it says that we have 3 degrees of freedom. But it's a bit of a tricky question. So it asks you if platform A is fixed or not. Can it actually move? Sorry, should I rewrite that? M6 n minus 1 5J1 minus 4J2. So we don't have any 1, 2, 4, or 5. 1, 2, 3, 4, 6. We have 5 bodies. 5 minus 1 minus 3. And we have 7 J3s. Right, so we have 7 joints. 24 minus 21. Yep. So it's actually a tricky question because with these, what you're changing between a spherical and a cylindrical joint is you're adding in 1 rotation from a translation. So we had this before. We also had the translation, but now we have rotation around that axis as well. So if the question is asking, can platform A move? You can, but that just means that your mechanism is loaded already. So that means that it wants to move, but it can't. So that imply internal stresses in your parts. So you don't want a negative M. Yep. So what I'm trying to say is there are 3 degrees of freedom in this box if there are sphericals, but the movements or the mobility is around this link there. So that just means that that link can rotate back and forth. Same with that. That doesn't actually do anything to enable A to move. So no, A can't move. I could top today. Cool. That's probably the hardest question you get from us. Just break it down to bodies, degrees of freedom, joints, and then chuck it in the formula. You should be fine. Okay. Let's go on with instant center of velocity. So the instant center of velocity tells us that there is a velocity between two or more bodies that are equal. So the way we teach this is we give you a 4-bar linkage. So 4-bar meaning 4 bodies, 1, 2, 3, 4. It'd be 4, 3, 2, and 1. And what instant center of velocity is simply, so if we have bodies 3 and 4, at this instant center, there is a constant velocity between the two. So at this point, there's a velocity that's constant between 4 and 3 that's shared, which is at that point. Similarly with 3 and 2, called I23. So at this point, 3 and 2 move the same. Same with 1 and 2, which is at this point, and same with 3 and 1. Oh, sorry, 4 and 1. I14. I should have drawn this down there. So these are the obvious relationships. 1, I1, 2. But there's also something, there's also a projected instant center of velocity. So there's not only are the relationships between 3 and 4 and 1 and 2, or the obvious ones where they're touching, there is an imaginary one which is projected. So if you combine these lines, at this point, there is a relationship of velocity between 1 and 3. 1 and 3. I13. Remember, if you're projecting, the furthest number comes first, I13. And there's also one here too. Pretending that these lines meet up, that would be I42. I42. So we use that to solve the next question. Okay, it says, locate the instant centers of the mechanism below. It says, if link 2 is turning clockwise of 60 radians per second, determine the linear velocity of point C using instant centers. So no trig, just instant centers. And it's easier than it looks. Let's do something for us. All right, redrawing it. All right, let's pretend that point meets. So this is 1, 2, 3, and 4. All right, so this is I, 2, 3, I, 3, 4, I, 1, 4, and I, 1, 2. This would be because 4 is further than 2, I, 4, 2, I, 3, 4, and I, 1, 4. What do you mean? I, 3, 4 is there.
So you know how there's an imaginary between I23 and I12, which is I42?
Between here and there.
Yeah, so that's I42. Is there no imaginary on that side?
Oh, you mean like this way?
Yep.
No, because they don't meet.
Ah, okay.
So there's only an imaginary point there because if you draw a line, they will meet at one point. Same with 1 and 3.
Makes sense.
I, 1, 3. So the question asks if this is rotating at 60 radians per second, how fast is this going to be moving? VI34. So A, D, B, C. If you get lost in my diagram, just go to the one there. E as well. You've got all your dimensions as well, but there's one missing. We'll go over that soon. So the first thing we have to do is we have to isolate I23 because that's the only bit of information. That's the only thing we can do with that bit of information. So we have the link between A and B. So we want to find how fast I23 is moving. So the way we do that is trying to find VI23, and that's directionless as well, equals how fast I want to. VI12 plus VI23 in respects to I12. So VI12 is simply the velocity of I12. So how fast is this going to be moving? It's not going to be moving because it's fixed. So equals 0. So next, VI23 in respects to I12 is that radial velocity times I23, I12. So that term there is just the distance between this point and that point. Or you could say a W2 AB, right? Because obviously V equals WR, right? So reiterating VI23. So the velocity of this instant center is equal to W2AB 60 times 1.2 equals 72. Oh, that should be centimeters. Okay, next. So this is I13. So we know that this is going that way. VI23, right? VI23, or 72 centimeters a second. So from that, we can get omega I3. Sorry, omega 13. Because our goal was to find this, right? So once we get that omega, we can use that radius to find the velocity. So the next step would be V I23 equals V I13 plus V I23 in respects to and this doesn't ever move. So that equals 0 because at instant center that doesn't move at all. Everything else is moving, but not that. It moves about that instant center. So W3 I23 I13. So RI23 and I13 would be from there to there. What is the distance between those two? So therefore, if we're just using these, VI23 and we have this and this distance. All right, yeah, so there's actually something missing in this tutorial. The way that you would find this distance would be to draw it to scale or print it and then measure it using a ruler. But obviously I can't do that. So I'll just have to give it to you. I23, I13 equals 4.07. And we've got that from a previous calc. 72 divided by 4.07 equals 1769. Cool. Our last step will be finding VC. So if we know that this 1769 last thing will be VC VI13. So that's that plus the velocity of C in respects to I13. So that is 0 because at instant senses it's 0. VC I13 is equal to W W3 times that distance between that and that C in respects to I13. And same with the previous calc, that should be measured using a ruler or to scale or SolidWorks. But for this example, I've got to give it to you. C in respect to I13 is 211. And we have W3, so all we have to do is multiply it. 1769 times 211. Centimeters per second. Cool. Therefore, VC is and that's our answer. Any questions? It's not too bad, is it? I don't think. Same as the other weeks. The key relationship you need to remember is V equals WR, and also V equals instant centers can be 0. If you find the relationships between the rotational speed you find the velocities, and then that's it. Yeah, I think it's pretty straightforward as well. How are we on time? Oh, 2 minutes left. Yeah, it's not too bad. Anyone have any questions about anything else? You should have your quizzes on opening tonight. So you guys have heaps of time to do that. I have one more week with you guys doing optimization, and then I'm going to pass you off to FEA guys. Yeah, and you guys still have like what, 3 weeks? Yes, it's not going to be that that vague. Focus more on identifying where the instant sensors are, especially the ways that I wrote the numbers. So if you've got 4 and 2 here, the instant sensor on the right is going to be I42. The furthest one has to come first, right? So I42, the 4 is further and the 2 is closer. Same with I13. The furthest number would be 1 and 3. If you're at I31 there, that would be implying that there's an instant sensor that in that direction, but there isn't. What else? For the quizzes, go through your supplementary and your lecture materials and define different kinds of linkages and mechanisms. So cranks, sliders, yeah, it's all in your lecture materials. Cranks, sliders, couplers as well. Couplers, ground, rockers. Everyone knows what a rocker is, right? Ooh. Have you owned one? You're sick. Other than that, I think we're good here. Thanks for coming. See you next week. Yeah, you too.